All right, good. So today what we're going to look at is this problem here. There's a differential equation problem. We have dy dx equal to e to the negative x squared with a initial value of y of 3 equals 5. Okay, so obviously we're trying to solve this problem here, and what we're given is there's some function y of x such that its derivative is equivalent to a non-elementary function, which in this case is negative x squared, e to negative x squared. Well, realize that this function right here is continuous from negative infinity to infinity, so you can plug in any x within these two points here. So the best way to approach these things it's gonna be a little tricky, but it's separable. So let's get dy by itself. We're going to do dy equals e to the negative x squared dx. Alright, so now what we're going to do is integrate, but we're going to do some tricky integration here. So let's integrate here. Next step I'll show you. We're going to put some bounds on this, and you'll see why here in a bit. So we'll start off with 3 here, and x. I'm going to do dy dt. Now t is just a dummy variable. Really, we should have x here for proper notation, but too many x's, a lot of people get confused. So t, again, it's just a dummy variable. It's not a big deal. It's not like you're introducing a new variable to the equation. So now we have this. This we're going to say the same. We're just going to keep the same. We're really kind of done working with this from here on out. It's this that we're going to take a look at. So you kind of notice you could cancel these and end up back here, right? If you cancel the two dt's, you would end up back at the dy. So what you're integrating here with respect to is obviously dt, and as we said, t is really equal to x. So anywhere you see a t in your head, you could replace t with x, and it would still be perfectly valid. We just use t as a dummy variable for easiness of doing the math. So you can kind of say, oh, okay, well, I'm not going to get too bogged down with the x's. So this right here, let's just look at dy dt, right? Again, it could be dy dx. It's equal to dy dx. This is the same. So what does this tell us? So this provides a lot of information. This is saying there's a function of y such that when you take the derivative, you get dy dt, dy dx. So there's some function out there, y of x, yt. There's some function out there that when you take the derivative of it, you get dy dt, right? So that's all that's saying. So let's integrate it. So we're taking with respect to t. We're going to get this function. We're going to get the next step from here is going to be y of t, and the bounds are going to be x and 3, right? And this is going to stay the same. We're just going to bring this down. There's really not much else you can do because, I mean, what's the antiderivative of this? Let's leave that here. Okay. So now we're going to plug in our bounds. We're going to treat it like we would any integral problem. So we're going to have, where we see these two bounds, we're going to be y of x minus y of 3. Right? And this, we're going to leave it as f. X 3 t squared dt. Okay. Almost done. Notice how we have y of x here. Now we have the function that we were looking for. Let's clean it up a bit. We're going to have y of x equals x to the 3 e to the negative t squared dt plus y of 3. Okay. Last but not least, what does y of 3 equal? Do you remember? It equals 5. So our final answer is going to be y of x equals negative x 3 e to the negative t squared. Again, t is just a dummy variable. Do not get bogged down with the t. This would be your final answer you would box. Now let's take a look at the final answer. This requires a second glance, more than just a cursory glance. So what we have here is a function, y of x, right? Again, if you're not familiar with this notation, this is literally just y of x. It could be, x squared plus 5x. It just means a function of x, right? You plug in an x, you get a number for y. That's all that means. You're probably used to this notation, f of x, right? They're the same thing. I could have wrote f of x there. But all this notation is saying that y is a function of x. Okay. So now let's look at the right side. We looked at the left. So now what we have on the right side, we have some indefinite integral of a non-elementary function. I have no idea what this is, but we don't need to know what this is. It's fine. We had y of 3. We know y of 3 is 5. That's what the initial problem said. So we're good there. But this is important. So let's plug in 3 for x, right? So if we plugged in 3, right, wherever we see x, you plug in 3. So you would say y of 3. Remember, because we had to get y of 3 equals 5, right? So we're plugging in y of 3 for the answer. We're going to say, so wherever you see an x, 3 e to the negative t squared dt, right, plus 5, right? Well, there's a property you may have learned in Cal 1 or Cal 2. If you have the same bounds, if these two numbers right here are the same, this integral evaluates to 0. It evaluates, so it's good. We're good. So whenever you plug in 3, this goes to 0, and then you just have plus 5, right? Which just equals 5. So we satisfied it. We found, we didn't find the function. And when you take the derivative of, you get this. But, you know, with computers, you could do it. You could plug it in, and you get it. But we did it pretty good. And, you know, on a piece of paper, we satisfied the following condition. When you plug in x is 3, you get 5. When you take the indefinite integral, and we created y as a function of x. So when you plug in a number here, so you plugged in another number, right? Let's say y is 7. You would get indefinite integral of 7, 3 e to the negative t squared dt plus 5, because that's the constant that we had. Plug this into the computer, it would give you some numerical approximation for this, plus your 5, and you have y of 7. So most importantly, we have a function. This is a function, right? It's a little different. You may not be used to seeing this, but it's a function, and we found the as close as we could the antiderivative of a non-elementary function such as this. So awesome, good work.